Hey guys, very good afternoon. Welcome to the case study discussion on Aileron Reversal and transport aircraft, where we are going to redesign the control surfaces which is having the transport aircraft, the primary control surface of rudder, aileron and elevator. This is because of the Aileron Reversal due to the critical condition of interaction of aerodynamics and the elastic property of the wing. Okay, and have the discussion of how the wing design is more critical, especially in the term of aileron reversal and the interaction between aerodynamic force and the elastic force. Then the placement of the control surface is more critical for controlling this aileron reversal. That will have a small discussion. Let's start our discussion.
Sure, sir. So coming to the problem statement, here we have come up with the problem statement of transport aircraft, where in this transport aircraft, aileron plays an important role when the aircraft moves in a high speed, which would create a reversal in aileron. Why? Because in normal conditions, aileron in the right side will move up and in left side move down, and for our aircraft it rolls right. But in high speed cases, it loses stability and automatically the aileron's right moves left, aileron left moves down, aileron left moves up, and aircraft rolls left side. In this case, it would be difficult for the aircraft design, so it is necessary to redesign it so that we can able to increase the stability and the safety measures would also be required.
Yes, sir. Talking about the root causes, sir. Now we should understand about what is happening. When the aileron reflects downwards, it increases lift on the wings, but it also increases the aerodynamic forces behind the torsional axis, which causes the twisting momentum on the wings. At high speed, dynamic pressure increases, and the aerodynamic loads also will be large. Flexibility of the wing twists upwards. Because of the twisting, effective angle of attack reduces. The lift which is gained by aileron also gets reduced, and sometimes lift becomes lower than the opposite wings. This causes the reversals, and main reason identified it is long flexible wings and insufficient torsional stiffness, large outboard ailerons, high speed cruise conditions, and lightweight wing material with the torsional reinforcements. Thus it causes the flexibility and aerodynamic interacted dangerousness.
The cause we identified is when the aerodynamic forces dominating the elastic forces, the torsional stability can decrease.
Yes, sir.
So that time is happening in the high speed operation. So where we have the total pressure over the aircraft static and dynamic pressure, where the dynamic pressure overtakes the torsional load, then the control reversal is happening. It should be the case. That is the what else?
So if you talk about the engineering analysis, our engineering team performed aeroelastic analysis. The step 1 will be the wind tunnel testing. Scaled wing model will move aileron tested at different speeds. Research shows roll effectiveness reduced rapidly after a critical speed. The step 2 will be film structural simulations. The finite element analysis revealed excessive wing twist near the tip regions. The step 3 will be reversible speed estimation. When the aerodynamic twisting moment exceeds restoration torsional stiffness, reversal starts off. Critical reversal speeds depends on wing torsional rigidity, span length, aileron size, and aerodynamic center position. Observed data are normal roll response below 420 km per hour and weak response near 510 km per hour. Reversal symptoms above 560 km per hour. This proved aircraft required redesign before certifications.
So for avoiding this this kind of aileron reversal, we have several methods. One is the wind tunnel testing, where we can model the scale down models and testing different RPM or different velocity of the flow condition. And second is the testing using models, fine grained modeling, where we can do the CFD analysis, where we can test the different span length and different aileron surface and different angles also. This is how we can do the testing before we are finalizing the model. And with this result, we can conclude that below the 500 is not the much effect, whereas reaching the 500 km/h velocity, then the aileron reversal start giving the effect. So we can scale down with this data. We can modify the control surfaces.
Now we follow to the solution part, and the solution parts have several solutions. By increasing wing torsional stiffness, we can redesign the control surfaces. For example, closing wing box reinforcement and composite torque skins and stronger spans or improves stiffness of the wing torsional. And secondly, inboard ailerons. When it comes to inboard ailerons, primary ailerons are moved closer to the wing load, where the structure is different there. And next solution is spoilerons assistance. Using spoilerons to roll at high speeds instead of only using ailerons. And differential ailerons deflection, that upward deflection, using upward deflection more than downward deflections. This reduces expensive lift and also twisting moments. And flyby control logic. This computer automatically limits the aileron angle at unsafe speeds. By these solutions, we have a final outcome of roll response improved to 30%, and also better passenger comfort and no reversing test angle.
Great discussion help us to understand how this aileron reversal is happening. The solution clearly explains the lightweight material is a major tarak mantra for aerospace, whereas coming to the very high speed and the aerodynamic phenomena, especially the aileron reversal, we need to modify the wing structure either by adding a differential aileron. The differential aileron will act as a one side, right side aileron reflect in smaller angle, whereas the left side aileron reflect in the larger angle. So this reflection will be different. That's why we are saying it's a differential aileron. And also we are using the additional support of the inboard aileron, the outboard aileron. In a wing we have three parts. One is the flap and the control surface aileron. And there we have inboard aileron or outboard aileron. Usually we are producing the rolling moment. We use the outboard aileron to produce a more moment. Whereas in the aerodynamic phenomena, whereas the control reversal, it is not sufficient to produce that much of rotation. So we are using the additional control surface of inboard aileron. So this is the assumption part we are arriving to controlling this aileron reversal or to avoid this aileron reversal. Okay. So this is how the case study helps us to understand. So redesigning the control surfaces as well as the flight, especially the passenger flight operation, high speed is very critical, especially the structural component, aerodynamic load compared to structural load. The aerodynamic load dominates in the aileron reversal. That is what the case study gives very finding for the engineers, also for the aircraft design. Okay. Thank you guys. We'll discuss in the next class.
Thank you.